Hello again, everybody, and welcome to another Geo-Institute live stream. It is the first of 3 Cross USA lectures to be delivered on the GI YouTube channel this summer by our Cross USA lecturer, Richard Bathurst. My name is Brad Keeler. I'm the director of the Geo-Institute, and welcome again to part of the Summer of Live. We have all kinds of great live streams, live events on our YouTube channel over this summer. Please be sure to visit our Eventbrite page to check them out. Registration is always free, and we would love to see you at one or more of those. If you don't know anything about the Geo-Institute, after you watch this today, cruise on over to geoinstitute.org, and there you will find out so many things about us, including that we are a technical society with about 12,000 members, most of whom are geotechnical engineers and or geologists, and that we are part of the American Society of Civil Engineers. And if you like what you see today, and Richard has worked very hard to make sure that you do. So even if you, I don't know what the agreement is here, but even if you don't like what you see today, you should say that you did and still click like, subscribe, and get notifications. And if you do those things, we will let you know every time we post something to the YouTube channel. The Cross USA Lecture Series is something that we started 15 years ago. That's why there's a 15 on all the things that we've been doing the advertising with this year. That wasn't just our favorite number. And we're gonna tell you a little bit more about that in just a moment. First, we have to say thank you to our sponsor of this year's lecture series, and that is GeoPeer. We have a brief message from our friends over there that we're gonna go ahead and play for you right now. Thanks again to GeoPeer for their sponsorship of the Cross USA Lecture Series. They have been a sponsor for the last 5 years, I believe, and we're thrilled to have them back with us every year. Now, here to introduce our lecturer today and tell you a little bit more about the Cross USA Lecture Series, it's Geo-Institute past President G. Han. G, welcome.
Thanks, Brad, for your classical and dynamic opening. Hi, everyone. It is my pleasure to welcome you to the 2024-25 Cross USA Lecture. I'm G. Han, Professor of Civil Engineering at the University of Kansas. The Cross USA Lecture Program, organized by the Geo-Institute of ASCE, provides distinct lectures to local GI chapters and the student groups across the United States. The program aims to enhance the prestigious of the geoprofessional by inviting outstanding scholars and engineers to share their expertise to various communities. The lecturers have been selected by the GI Local Involved Committee, the GI Graduate Student Leadership Council, and the GI Board of Governors, based on individuals' professional achievements, lecture ability, and the prestigious within the geoprofessional community. This year's Cross USA lecture are given by Professor Richard Bathurst. Dr. Bathurst received his BS, MS, and PhD in civil engineering from Queen's University, Canada. He is currently Professor Emeritus of Civil Engineering at the Royal Military College of Canada and holds a cross appointment at Queen's University. Dr. Bathurst made a contribution across a diverse range of applications, from micromechanics of granular soils, the use of geosynthetic metallic reinforcement in earth-retaining systems, seismic performance probability, reliability-based design, and reinforced and unreinforced soil structures, and the load and the resistance factor design calibration of soil structures. He is a frequently invited speaker and a keynote lecturer. While his awards are too numerous to list, I will note that he was the 2021 recipient of the ASCE Geo-Institute Thomas A. Middlebrooks Award for the best paper published in the ASCE Journal of Geotechnical and Geo-Environmental Engineering. He has also devoted numerous hours service to our profession, service on the committees for developing of the code and the standard authoring technical manuals, and serve as editor-in-chief of the peer-reviewed technical journal Geosynthetics International and the ASCE International Journal of Geomechanics, and as the president of multiple engineering societies, including Canadian Geotechnical Society, International Geosynthetics Society. Dr. Bathurst is a fellow of the Royal Society of Canada, which is the highest academic honor that can be bestowed on a Canadian. The International Geosynthetics Society established the Bathurst Lecture in 2021 in recognition of his lifetime contributions to the development of geosynthetic soil reinforcement technologies and the mission of the IGS. He was recently awarded the 2024 Julian C. Smith Medal of the Engineering Institute of Canada for achievement in the development of Canada. To know more about Dr. Bathurst and his career, you may read the Geo Legends article published on the June and July 2025 issue, which is the latest issue of GeoStrata. After reading his article, you will learn valuable lessons and advice from him that may help you succeed in your professional career. On my personal note, I have known Richard for nearly 30 years and admire his great achievement in our profession. I visited him at the Royal Military College of Canada in 2000 and saw the very impressive full-scale retaining wall test facility there. I'm sure he will discuss full-scale MSE wall tests use this facility in his lectures. I'm very fortunate to have had an opportunity of teaching a short course with Richard in Hawaii last January, and then having some fun time together. Now it is my great honor to welcome Professor Richard Bathurst for delivering today's Cross-USA lecture, Numerical Modeling, Understanding of MSE wall Behavior. Richard, please.
I'm just getting my machine. One second. All right. Swap screens here, just a sec. So my hope is that you can see my full screen.
Yes.
Okay. So thank you, G. Thank you, Brad. Thank you, the ASCE Geo-Institute, for giving me this opportunity to speak about numerical modeling to improve understanding of MSE wall behavior. Now, mechanically stabilized earth walls are well known, and they are a well-established earth improvement technology. They're characterized as gravity structures comprised of a reinforced soil mass with horizontal layers of either relatively inextensible steel reinforcement or relatively extensible polymeric reinforcement materials. And in this slide, you can see an example where the soil reinforcement material are steel type. And you can also see the reinforced soil zone and the facing treatment, which in this case are reinforced concrete panels. Other soil reinforcement materials include woven geotextiles. An example is shown here. In fact, this slide here shows a very famous wall because at the time that it was constructed, it was the largest geotextile wrap face wall in the world, and it was used to support the sides of a preload at a construction site in Seattle. And you can see the cross section comprised of this reinforced soil zone and these horizontal layers of geotextile reinforcement. So this is what I mean. It's a composite structure, and it's essentially a gravity structure. More frequently, we see the use of geogrid materials manufactured from HDPE and polypropylene and polyester. And there are many of these types around today and used to perform, again, the reinforcement function, where the reinforcement serves to stiffen and strengthen the soil behind the wall. Here is a pic. Oh, I can't believe it. Here is a slide showing a HDPE geogrid being placed during construction, and you can see how it's attached to the back of the panel facings. And in this case, it's being pre-tensioned before it is covered with the backfill soil. So why numerical modeling? Well, we may need to carry out numerical modeling for the design of a project-specific MSE wall that is unusual or subject to extreme loading and or a critical structure. And here is an example of the latter. This is again a very famous steel strip MSE wall, 46 meters high, and it was constructed at the end of one of the runways at the SeaTac airport near Seattle. And you can see it's quite a substantial structure. The inset picture shows the components of this structure. And this structure was built and designed in a highly seismic area. And for that reason, there was a need to examine the mechanical performance of this structure under extreme conditions, including earthquake. And here's a slide that shows the 2D flak model that these folks used to analyze this wall and to ensure its stability under earthquake loading. A second reason we may carry out numerical modeling is to gain insight into the mechanics of the behavior of MSE walls. So, for example, if we have a good model, we can learn things like, for example, what are the strains in the soil? What is the distribution of load in the reinforcement layers under operational conditions? You know, these are things that are difficult to observe from physical models, as I'm going to demonstrate later. A third reason for numerical modeling is that we can use these models to fill gaps in measured performance of instrumented walls constructed in the laboratory or in the field to refine or develop new design models. Here is an example of of a test wall that was built some years ago, and it is part of a larger database that myself and my colleagues have developed to guide the development of more accurate design methods for the internal stability of these systems. And what one can do with this data is you can predict what the maximum load is in a reinforcement layer using your favorite model. For example, it might be the ASCE simplified method, where there's a chart in which you can extract the equivalent earth pressure coefficient, put it into this simple earth pressure like equation, and predict what the maximum load is in each layer. And then one can take the measured values, for example, from that wall that I just showed you, and plot the measured values against the predicted values. And what you see is there's often a lot of scatter. And here we can see that the measured values, at least for these geosynthetic walls, tend to be lower than the predicted values. But gathering this type of data is expensive. So a strategy to gather more data or to examine some of the influences of the different components and the geometry of these walls on these predicted and measured loads, we can carry out numerical modeling. And here's an example. Again, here we're plotting, in this case, predicted load against measured load. And the red crosses that you see here are from physical data, like that field wall that I showed you earlier. And then the other symbols are predicted values from similar type walls from numerical modeling. And so you can use the numerical data to fill in the gaps in these types of presentations. And also you can use the physical data to check that the numerical models are giving you reasonable results on a case-by-case basis, but also statistically as well. So synthetic data is very useful to fill in the gaps in measured wall performance databases, which have been collected and published in the literature. A fourth reason to carry out numerical modeling is it can be used to carry out parametric sensitivity analyses. I'll give you an early example. This slide here shows the first instrumented steel strip wall constructed in Japan, in this case in 1978. So all of those steel strips that you see in the cross-section were instrumented. And myself and my colleagues, led by Yan Yu, wanted to make these load predictions, but we didn't have all the data that we needed to load our numerical model. In particular, we didn't know what the backfill modulus was or the foundation modulus for the soils that were involved. And to overcome this deficiency, we tried different combinations of the bulk modulus in the reinforced soil and in the foundation soil. And by trial and error, we got a combination of these two elastic moduli that gave us the best fit between the predicted values, which are these continuous lines that you see here, and the measured values. So this was an example of using numerical models to backfit problem input parameters that were not easily available. We can also carry out parametric analysis for walls having different facing reinforcement and geometry using numerical models that are validated against instrumented, high quality, full scale physical models. So, where do we get these physical model test results? Well, fortunately, and G alluded to this, over a number of years, we constructed full-scale reinforced soil wall models in the RMC retaining wall test facility, which is a substantial size. And here you can see the exposed facing of one of these walls. And actually, in another seminar that I'll give, webinar, I'll talk specifically about this loading program, because there's lots of great stories and lessons to be had from that program. But anyway, when you have all of these test walls available to you, you can then systematically investigate, well, what is the effect of the facing batter, near vertical, battered? What if it's a wrap face, which is relatively flexible? What if it's a concrete panel type wall? So having these physical examples and the measurements from them, you can then take the physical model that you see here and transform it into a numerical model. And in this case, what we're looking at is one of our FLAC numerical models. But there are challenges and pitfalls, okay? There be dragons when carrying out numerical modeling of MSE walls. And here are the challenges. The first is deciding on how to model the stiffness of the reinforcement under operational conditions. And we need to know the stiffness, because in simple terms, we need the stiffness so that the program can use that stiffness together with the strain to predict what the loads and the reinforcement are going to be. So a question, and this is a challenge because reinforcement geosynthetics, the plastic polymer type of reinforcement, are rate dependent to different degrees depending on the type of reinforcement. So this means that the tensile stiffness is load, strain, and time dependent. And assuming a simple constant linear stiffness is problematic and arguably just plain wrong. So you can understand that by simply carrying out a tensile test using standard equipment like in the photograph on the right, and pulling on this specimen at different rates of displacement. And if you look at the dashed lines in this tensile load versus tensile strain plot, you can see quite clearly that tensile mechanical response is quite sensitive to rate. This is particularly true for polyolefin type reinforcement materials. It's less of a problem for polyester type. So the question is, how can I develop a model that handles this rate dependent nature that I've just spoken about? Well, one is the best approach is to gather data from constant load creep tests. And from these constant load creep tests, which are shown on the left here, strain increases with time, and load. And from those constant load creep tests, we can generate a set of isochronous load strain curves, load versus strain at different times. And here I just want to emphasize again that a constant rate of strain test at 10% strain per minute does not have the same appearance as these isochronous load strain curves taken from constant load creep tests. From these isochronous load strain curves, we can fit a hyperbolic model that captures the nonlinear trend that you see in these plots, and can be used to develop a stiffness model. This slide here shows the stiffness of the reinforcement as a function of time and strain, and this hyperbolic model that I showed earlier can be simply rearranged in order to show the influence of strain level and time on the stiffness of the reinforcement. So just, you can see the stiffness here is proportional to the load divided by the strain. And it's this stiffness model that needs to be used in your numerical model. And the magnitude of the stiffness can have a powerful influence on the development of load and strain in the reinforcement. So what you're looking at here is a numerical model, and we're looking at the magnitude and distribution of loads in the reinforcement layers as we go from the top of the wall to the bottom. And you can see that as the stiffness of the reinforcement increases, there is an obvious increase in stiffness, particularly over the bottom of the wall, indicating that in this example, the stiffness of the reinforcement is very important to the outcome, in this case, predicting the maximum load in each reinforcement layer. Other challenges, soil properties, and this is not unique to MSE walls. Here, what you see are a series of triaxial tests and plane strain tests. And the triaxial tests are quite familiar to all of us, at least qualitatively. And one of the challenges with our granular soils is they're highly nonlinear and stress dependent, and you can see that in the curvature of the physical data. And different models can be used to model the soil, and they range from something simple like a Moore-Coulomb type of model here to a more complex model like the Latte model, which arguably is the holy grail for constitutive models of granular soils. But they have increasing levels of complexity. The Moore-Coulomb model is relatively simple. Latte's model, if I've counted all the parameters correctly, requires 12 parameters, which sometimes can be difficult to get. But it's interesting that if you're interested in walls that are under operational conditions and the strains in the soil and the reinforcement are quite low, you can often get away with a simple linear elastic plastic model. As long as you're able to get a reasonable estimate of a single value of the elastic modulus. And that's because we're operating at very low strain levels. And, maximum strains in geosynthetic reinforcement materials under operational conditions are almost always less than 1%. So this is evidence in support of how we can simplify our models by simply using linear elastic Coulomb type models. Connections. What you're looking at here is one of the SR-18 walls in Washington State. This one is 11 meters in height. You can see a cross section here. And again, it was heavily instrumented. And this wall gave us the opportunity to develop a FLAC numerical model. And you can see the FLAC numerical model in the bottom right here. It's quite a large model and quite sophisticated. And so one of the things that had to be addressed was how do we model the connections between the reinforcement and these modular block facing units. In the top left here, you can see the facing units and you can see the reinforcement. And, one needs actual physical data in order to develop simple models for in the vicinity of the connection. So ideally, you carry out in the lab full-scale tests, and these can be shear type, in which we push one block over another with or without the reinforcement at the interface, and you can develop an envelope for the shear capacity of this interface that you can then put into your model. You can also use the same tests to develop the stiffness of that interface, the shear stiffness. Also, we need to know what is the connection strength and the stiffness of that connection. And that again could be established from physical testing using similar type of equipment to the slide, the pictures I just showed you. And here you can see normalized connection load plotted against the displacement recorded at the connection between the reinforcement and the modular blocks, and you can fit a load level dependent model comprising a linear portion and then a maximum tensile strength capacity component. There are other types of connections. For example, these polyester strap reinforced soil walls are becoming more popular, and you can see the connections that are formed for this particular system where the reinforcement material is passing through a loop type connection. So one may want to understand how to model that, what can be a fairly complex system. And thanks to my dear friend Dr. Damians in Barcelona, he actually did some full-scale tests. Here you see the panel on its side, and the connections, 4 connections are being loaded at the same time. And here you can see the test apparatus, which is quite substantial. And then Ivan and his colleagues made a 3-dimensional model to test their 3-dimensional model against these physical tests. The connection type and the modeling can influence the numerical model outcomes. Here is, again, this is another test from the RMC suite of full-scale tests. You can see cross-section schematic on the left side, and you can actually see a photograph of this wall after it was surcharged to failure, and the facing just blew out after the surcharging was completed. So the question then is, how can we use the numerical modeling to learn lessons about the behavior of these connections and the distribution of load and strain in the reinforcement in proximity to these connections? And what you see in this slide here are the distributions of reinforcement strain from the back of the wall to the end of the reinforcement for the different reinforcement layers. So layer 6 is close to the top and layer 1 is close to the bottom. And the symbols are the measured data. And the continuous lines are the predicted strains. And these can be predicted using a hyperbolic model of the type that I showed you before. And, these predictions are judged to be reasonable. I mean, these are complex systems, but from a practical point of view, the predictions are useful and reasonably accurate. And what the models show is that the strains in the reinforcement close to the connections are actually generally the highest strains, rather than the expectation from the past that the highest strains might be somewhere deeper in the reinforced soil mass. And the question is, why is that? Well, the reason is that As this wall is being constructed in the real world and numerically simulated in our models, the soil tends to move downward with respect to the more vertically rigid facing system. And that puts additional loads on these connections that would not be there if the soil and the panels could move together. So this numerical modeling helped us to understand what was happening with respect to the behavior of the reinforced layers. Soil reinforcement interfaces. So when we look at our numerical model, we have to model the transfer of load between the surrounding soil and the reinforcement layers. And we usually use some sort of interface model with shear stiffness springs and normal stiffness springs. But it's often difficult to back calculate what those values are from simple element tests, including pull-out tests or interface shear testing, because you have limited monitoring points and you can't see anything because the soil is opaque. So one of the things that we did, which is sort of fun, is we developed a transparent soil methodology. And what we did is we took a dry fused silica quartz material and we mixed it with a fluid which has the same refractive index. And the outcome is that when the soil is dry, it looks a little bit like granulated sugar, but when you inundate it with this matching liquid, it becomes transparent and you can see through it to a certain distance. So for example, you could observe the presence and the behavior of a geogrid which is embedded in this material. So we built a pull-out box, a fairly large one, you can see by the dimensions here, 3.7 meters in length. And we embedded specimens of geogrid in this transparent soil. And we observed the behavior of the reinforcement by looking up through the bottom of this pull-out box, which had a transparent plexiglass base. And we could surcharge the specimen, and then we would pull on it as you would in a conventional pull-out box test. But the neat thing is we could watch what was happening. And what you're looking at in this photograph is, you imagine you're lying on the floor underneath this pull-out box and you're looking up and you can actually see the grid and some painted tracking particles. So this is the pull-out specimen, and this is a front clamp which pulls on the reinforcement, pulls the reinforcement through the transparent soil. And keep your eye on the red line for point of reference. And what you can see is, as the reinforcement is being pulled towards the left, you can see it stretching. Okay, and stretching. And finally, at the end of the test, the reinforcement actually breaks. It's not listening to me. Okay, I think it's just a little bit sluggish. Anyway, it'll snap at this point here. And we can take that data because we can use DIC to digitize this data. What you're looking at here is the same specimen that you just saw in the previous movie. And as the test progresses, the reinforcement at the front of the specimen is largest, and then the displacement diminishes as we move further to the back of the reinforcement. And at some point, you could argue around 400 millimeters back from the loading clamp, all of the load has been dispersed. So this provides a huge amount of information to develop interface models between the reinforcement and the soil. And from this data, and I don't want to get into large details about the model, but the physical data points have been deduced from the digital, the DIC technique. And what you see here is the model, which is following very neatly that performance. And so this model provided us with a shear stiffness parameter, which is displacement dependent, that could then be put into our FLAC models to capture this particular geogrid soil interaction mechanism. Boundary conditions. For example, MSE walls will experience some reaction or resistance developed at the toe of the wall. And we, in our RMC full-scale wall tests, we actually instrumented the bottom or the toe of each wall so that we could record what is that load, what is the magnitude of that load during construction and during surcharging, and we could compare that load to other similar walls that had different configurations. And here is an example of a parametric analysis. The symbols represent different reinforcement layers, and the location of the reinforcement layer has been normalized with height of the wall. So this is the top of the wall, and then we go down to the bottom of the wall, and we can predict what the reinforcement load in the reinforcement is at any stage during the test. So using a calibrated FLAC model, we then reduced the toe support and numerically. And what you can see here is as the toe support decreases, the load in the reinforcement goes up. And the neat thing is, one of the lessons that you can learn from this is that, however, by the time you get up about halfway up the wall, the reinforcement layers are not feeling the effect of this decreasing toe support. So this gave us some insight into the significance of the magnitude of the toe support at the bottom of these walls. Another issue with respect to the influence of boundary conditions is the foundation compressibility. So an MSE wall will sit on a foundation which can have different levels of compliance. It could be rigid, or it could be a soil which has some compressibility. So we did some numerical modeling where we modeled the influence of the foundation compressibility using linear springs, in order to simplify our interpretation of the results. And here are some results, a little bit busy. Two types of reinforced soil walls, one with polypropylene geogrid, one with welded wire. And we changed a whole bunch of stuff. We changed the height of the wall. We changed the stiffness of the foundation. And if you look at the bottom plot, it's just one example. You see there's three sets of data here. And these are for the same wall, but with different foundation compressibilities. And you can see that as the foundation stiffness increased, the load that went onto the reinforcement layers decreased. So there was interplay between reinforcement load and foundation stiffness that really can only be examined using a careful numerical model. In addition to modeling the horizontal toe load, we also measured the vertical toe load coming down on the wall. And what happens is that during construction, let's look at the top diagram you see here. As the wall increases in height during construction, the vertical toe load increases. Not surprising. But what you can see here is that the measured vertical toe loads actually increase at a greater rate and non-linearly. Why is that? Because this is the down drag effect that I spoke about earlier, where the soil hangs up on the reinforcement at the connections, and this develops additional load. So in addition to predicting and measuring the horizontal loads, we can do this with the vertical loads, and using different soil constitutive models, we can try and predict this performance. And you can see in this particular comparison that the measured and the predicted loads were in a great sympathy, and showed that really the soil model really wasn't important. And that's largely because this is just a vertical weight equilibrium problem. The constitutive model is less important. That is for the soil. And if you combined all these things together, you can see that the influence on the reinforcement loads of reinforcement stiffness, soil model and friction angle, and toe support all play together to influence the magnitude of the reinforcement loads in the reinforcement. Now, so I don't want you to focus on any particular plot that you see here, but the message is that you can see how the reinforcement tensile response is influenced by all of these parameters that I talked about before: the stiffness of the reinforcement, the soil model parameters, and the type and the magnitude of the toe support at the bottom of the wall. All of them play together, and really to understand these effects, a well-posed and accurate numerical model is required. In addition, from these physical model tests that I've showed you, we measured the vertical contact stress between the reinforced soil and the concrete foundation of these models in our laboratory. And again, what we could do is compare the predictions of these contact pressures at the foundation with the measured results. And here, let's just look at this top plot that you see here. The symbols are the physical measurements, and the smooth lines, the continuous lines, are the predictions. Now, first of all, and this value here is the vertical pressure at the bottom of the wall. So generally speaking, we largely captured, at least qualitatively, what's going on. And again, the numerical model was in sympathy with the physical model, which showed that there was a relatively low contact pressure directly behind the wall. And again, this is another symptom of this mechanism where the soil tends to hang up on the back of this relatively rigid wall as the soil is placed, compacted, and the wall moves outward. Compaction. In the real world, we use compaction equipment behind the facing to densify the soil and improve its mechanical behavior. And we did the same thing in the RMC retaining wall test facility using lightweight compaction equipment. And this led to the challenge: how do we model that compaction? So here is an example. This wall in the photograph is a wrapped face wall, and you can see the cross section of the wall with the wrapped faces, and this is the numerical model attempting to represent what we constructed. And the technique that we came up with to handle the compaction effect was that at the end of placement of each 150 millimeter lift of soil, we applied a transient uniform surcharge pressure. And then when the layer was completed and before the next layer was constructed, we removed it, and then we repeated the process for the subsequent layers. And this tended to, this created a load-unload cycle that is an analog to what would happen to the soil in the field. And we use different transient surcharge pressures to capture the effect of the size of the compaction equipment. So that's how we handled compaction. Now, numerical models will always give results. And sometimes, often they'll actually give fantastically wonderful cartoons. However, what is important is to ask yourself, how robust is the numerical model across multiple wall scenarios, having different facing reinforcement and geometry? So often what I read in the literature, folks carry out numerical parametric analyses on MSE walls, but they only compare their model against, one set of model results, one wall geometry type, and often just for one performance indicator, maybe the strains in the reinforcement. And they come back off that and say, listen, my model is good. I can use it to investigate other things like geometry, reinforcement, soil. But what you need to do is you need to check the veracity of your model, not only with strains and loads, etc., but also those measurements from multiple walls having different facing reinforcement and geometry. And if you can do that, then I will accept the veracity of your general numerical model. And where can you get this data? Well, there's about 14 of these RMC full-scale MSE walls that have been constructed and published. Some of these walls have more than 350 pieces of instrumentation and measurement points, so there's no excuse not to test your model against any one of these walls or multiple walls before you embark on your parametric numerical analysis. Here is an example. There are two columns of data here. One is for one of our walls that was constructed with a polypropylene geogrid, and here's another one with a welded wire reinforcement. And what we are interested in this particular study was looking at the influence of different soil models on the predictions of strain in the reinforcement and their comparison with measured results. So what you can see is that in general, again, we judged that the predictions were in reasonable sympathy with the measured results. We also deduced from these particular tests that we didn't really have to worry too much about the actual constitutive model for the soil we used, because we were dealing at the end of construction life of the structure, where the strains in the reinforcement are quite low. The other thing you can see in these slides, you can see the measurement points. They have range bars on them, because most people try to put their predictions through a single best estimate of a measurement, but it's best and much fairer to try and pass your predictions through a range, a confidence range in the measured predictions, and that's what you see here. So in conclusion, what I've hoped to do is in this presentation is to identify the challenges to numerically modeling the quantitative performance of MSE walls under operational conditions. And to meet that objective, I have identified particular challenges. And I've ended my presentation with the need to check the veracity of model outcomes with measurements from multiple walls having different facing reinforcement and geometry before one jumps into a large, complicated parametric analysis. So I just want to close by acknowledging that this work was not done in isolation. There have been a number of co-conspirators, postdocs and various professors, and my dear friend Tony Allen, who have been involved in this work over a span of what is now approaching 2 decades. And for them, I'm very grateful. If you're interested in the work that I've done, I have a website where you can find these papers. I'm also easily found on the internet, and I'm happy to send you papers or to answer questions that you might have in your future numerical modeling activities. Thank you very much.
Excellent. Thank you so much, Richard. That was fantastic. And so now what we would like to do is open things up to questions from our audience. So if you're here and listening, we invite you to put questions into the chat, and we will have Richard answer some questions for us. So to get things started, we've got a couple of questions here. I wonder, Richard, if you could tell us a little bit about modeling these walls for seismic behavior. Can you talk a little bit about the work that you've done there?
Yeah, and no, we haven't rigged this, okay, but I do have some spare slides in my pocket if I can just share my screen again.
Oh, I think Richard pressed the leave button instead of share.
I think we just lost him. Hopefully.
Well, he'll figure that out pretty quickly, and he'll be back. And I don't know if you want to wax poetic on the Cross USA lecture while we wait for Richard to get back in here, Susan.
You know, I will for just a couple of minutes. So I will say I think Richard is one of the perfect examples of who is ideal for this lecture, because I think when you look at the work that he's done through his career, he's got such a great foundation that ranges from academic theory all the way across to practice, from the laboratory scale through to the field scale. So I think he's really remarkable in terms of the contributions that he's made to the profession. And so I think his the applications that he has and his settings as the cross-country lecture have been ideal. So it's what a wonderful pleasure to have him deliver the lectures this year. So please, definitely, as you look for folks to come in and to nominate in the future, definitely think about someone who fits those kinds of models as well, too.
Well, I was kind of hoping that would buy us enough time to have Richard back here, but no. Oh, here we go.
There we go.
Richard is back.
I don't know.
That share button is perilously close to the leave button, and I think that's what happened. But
I'm glad. I'm sorry that okay. I'm going to try this again. I'm so sorry.
Good.
There we go.
Okay,
We're back.
I'm sorry for that. Okay, I'm going to just go down here, and so the question was, have you done any seismic stuff? And the answer is yes. We actually have a shake table at RMC, and there's a bunch of publications in which we have carried out reduced scale tests. Now, they're not, I'm sorry, they're not like 4 meters high. They're usually about a meter and a half high. And there's a bunch of publications where we took, those physical tests and compared the results to predictions. And here's an example of using one of these calibrated models. And again, it's a numerical FLAC model, which was carried out by my dear colleague Kianush Hatami at the University of Oklahoma. And here, this is just like a snapshot in time where this wall is moving back and forth, and you can see the development of a sort of a bilinear failure mechanism, which is developing in this numerical model, which again is not dissimilar to what we have observed and what other folks have observed in these physical tests. So that's the short answer. Yes, we have done numerical modeling of earthquake challenged MSE wall structures.
Excellent. Yeah, and you made me remember, so I took a visit to RMC. You were unfortunately out of town when I visited, but the folks from Queens took me on a tour of your facilities while I was there. And the experimental facilities you have there are amazing, right? So you've got the scaled model set up, three-dimensional lab testing that you're doing. I'm curious to know if you've done three-dimensional modeling based on those tests that you've performed as well as the extensive field testing that you've done too.
Well, fortunately, all of the structures that we have constructed, the reinforcement was planar and continuous in the horizontal direction or in the running length of the wall face. So we didn't have to worry so much about three-dimensional effects, but we have with my colleague Ivan Damians at UPC, we did carry out three-dimensional model testing, and you can see it here. This is using a 3D package, which is called CodeBright, and so here you can see, this three-dimensional issues where we have just a bar coming out of the back, and this posed a whole bunch of challenges. One of them is the numerical domains are huge. The level of discretization is huge, but we learned some interesting things. For example, I've got a bunch of slides here. For example, what you're looking at now, you're looking face on to the back of a reinforcement panel, and this red bit here is the steel strip that's attached to it. And this plot that you see here shows the distribution of vertical stress at the elevation of that reinforcement. So the vertical stress is moving along neatly at this level, and then all of a sudden, the vertical stress acting on top of the steel strip is elevated, and then it goes back again. And again, this is the same thing. What's happening is there are parasitic loads that act near the connections with the reinforcement, and this is difficult to capture.
Mm-hmm.
So what we were able to find from this is that if you have a continuous layer of reinforcement strips, if you can see my cursor there, you can simulate that row of discrete strips as an equivalent continuous horizontal inclusion. But when you need 3D modeling is when it's discontinuous. So here, for example, we can see there's 2 bars here, then there's 1 bar here. Where I've highlighted in this oval here, you can see 3 bars, then 2 bars, 3 bars. So then the effect, the 3-dimensional effect, actually develops, and that encourages one to try and use 3D models, but they're expensive and time consuming.
Yeah, that makes sense. One thing that's always interested me about your work, Richard, is the let's say the comprehensive approach that you take from lab scale to field scale to numerical modeling, right? So a lot of times people do one aspect of that and focus completely on that. I wondered if you could give us insight into if that was that a conscious decision on your part? Did you actively cultivate coming in from all of those approaches, or was it something that you felt like you needed to bring in all of those things to answer a question completely?
I think a lot of it was opportunity. I would like to claim incredible brilliance, but what actually happened was I hooked up with Tony Allen at WisDOT, Washington State Department of Transportation, and he was leading the mission to develop new design methods for these systems. And he was able to cobble together funding from a consortium of 12 departments of transportation in the States. And I was able to get some funding from funding agencies in Canada. And by the time we put all the money together, we had 11 years to build these walls. Each wall was a master's thesis. And it just led naturally to, okay, we've got these tests, they're expensive, we're going to have to stop doing them. Let's go to the next phase and use these tests to validate and develop models. And then we can use the synthetic data to fill in the gaps, and also to develop models that we could start investigating the performance of these walls within a statistical framework. So really, one thing just led to another, but it was just good fortune, being in the right place at the right time, having friends who had money, and being able to carry out, which has a very long-term project, as you imagine. The very first wall ever built was in 1988, and it was the result of a prediction symposium funded by others, where they said, okay, let's gather all the self-proclaimed experts in the world. We'll build some full-scale monitored walls, and then we'll ask them to make predictions of the results. And that was how I got the test facility. So again, there's a long story, and I can tell it in one of my next webinars, actually the next webinar. I'll just talk specifically about these tests. And it's a very entertaining story, I believe.
Yeah, excellent. Yeah, I think your commitment to seeing that through to application and practice is admirable too. So let's go to some questions from the chat. So Amin B asks, to model the compaction, would you support using vibratory compaction modeling after the method of Seed and Duncan?
First of all, their model is much more complicated, and secondly, their model was developed for rigid wall scenarios. The thing is with these MSE walls, and also even for these steel reinforced walls, the facing has some compliance and flexibility. So the predictions that you get from their model, which was not for reinforced soil systems, tended in our experience to overestimate the effect of compaction. I should say that this compaction model we're using is a methodology. It doesn't really capture what actually happens in real life, where the compaction load is moving across the surface, and there's a temporal aspect to it. It was a useful, practical method that gave the right answer at the end of the simulations.
Yeah, it's a tricky process.
It is.
To capture for sure. So Harach Agopian asks, is the stiffness method adopted by state and federal agencies? And when can they come into effect?
The stiffness method is currently in the ASCE specifications, the bridge design specifications. So 2020, you can find it there. It has been adopted by the Canadian Highway Bridge Design Code, which is our equivalent to the ASCE code. So it's there. And in fact, in the ASCE code, there is a detailed explanation of how to use it. And it is used to predict the loads for MSE walls under operational conditions.
Excellent. Good. So can you tell us about any numerical modeling you've done for other types of geosynthetic walls than what you've talked about here today?
You and I must be telepathic. One of the other types of research that we've done is we've looked at geofoam seismic buffers, and these are the use of geofoam, which is polystyrene, in which you pack the panels of styrofoam panels up against a rigid wall, and it acts as a buffer so that when earthquake loads, the horizontal component of earthquake load slams into the back of that rigid wall, that material acts as a cushion. And what we were able to do is to develop shaking table models to simulate that problem. And from those shaking table tests, and I could speak a lecture on this, and I have in the past. Here, for example, our comparison of physical loads on the back of these walls with the numerical, and we used a FLAC model. And just to get to the punchline, at the end of the day, we were able to take that calibrated numerical model, scale up the problem to full scale for walls of different heights. You can see here 1 meter, 6 meters, 9 meters. We then loaded these walls with different frequency content and magnitude from earthquakes, and we came up with design charts. And these design charts can be used to tell the designer, what stiffness and thickness they need to optimize the seismic buffer performance of these geofoam inclusions.
Excellent. Great. Well, Richard, we are so grateful to you today for spending your time with us. I think we're running up on our time window here. So with that, we will wrap it up. But great thanks to you for everything that you've done for us. And I'll turn it over to Brad to take us out.
Absolutely. That was fantastic, Richard. We really do thank you again for doing that. And it's been a fantastic year having you as Cross USA lecturer, and you're kind of fun too. So we like having that to throw into the mix. I put up on the screen our Eventbrite page. If you haven't visited it yet, I mean, you probably did because you managed to register for this and show up. You can register for any of our live streams at Eventbrite. They are 100% free. There's all kinds of good stuff coming up. Our next event, as you can see there, is the premiere of our next Geo Legends video episode. It'll be featuring Patricia Culligan from the University of Notre Dame, interviewed by Marika Santagata of Purdue University. That's July 10th. You don't want to miss that. We have a special session on PE licensure for geotechnical engineers on the 15th, GeoStrata Extra on July 17th, and then our next Cross USA lecturer from the very Richard Bathurst, who presented to you today, on July 22nd, and all kinds of other amazing stuff throughout the Geo-Institute Summer of Live. So thanks to all our viewers for being here today. Again, if you liked it, and you probably did because you're here at the end, click like, subscribe, get notifications. And if you do those things, it means we will let you know every time we post something to the YouTube channel. Richard, very good job today. Thank you for that amazing presentation and for your smooth recovery after you accidentally left the meeting. That was good too. Susan, great job.
You never have 100% success. So I'm thinking perhaps the next one will be perfect for all of us.
Susan, thanks for moderating today. And our producer was Aurora Flieger. We will see you in 2 weeks with the next Geo-Institute live stream.